Okay, is this recording? It's recording in the document, but we have it on the PC. So. All right. Where is the Zoom meeting just showing the document?
Oh, is it showing the document?
Yeah, if I have it on the PC, why is it not showing?
Well, this doesn't change then. Oh, this doesn't do anything to Zoom. If you want to change things, you change in Zoom itself.
All right. So show me where we're doing that there.
So I mean, the camera's pointing. The camera's, yeah. Click on the little arrow next to the camera, and then change to that. Yeah, that's the. There you go.
Okay.
So that's how you.
That's what I went
for.
Okay.
Yeah.
Okay.
What is it? I think the dot camera shows up as wolf vision. Yeah. Wolf
That's
vision
fine.
is a
I want
dot
it on this one.
And then
here,
that's the
because when
camera.
I show it up there on the doc cam, they'll still capture it.
Yeah.
So I don't have to switch back.
Yeah. So that's how you. Just
Okay.
that little area, you see all your different options.
So we'll just need to adjust the camera.
Yeah. Yeah.
Here, I'll switch it over to. I go back, right? If there's any way to zoom in and kind of fill in that screen, that'd be great. I'm pretty sure we've used the Zoom before on that. Like I said, I've been that close, but maybe it has. Maybe it's been taller. Maybe we've had it. Yeah, I think we've had it raised or something. Madison, you good?
It's engineering, but then I didn't know we got it anymore, so I just.
So we'll record it anyway.
Okay.
Since we got it all set up.
Okay, I might, just depending on how I feel. Just because my science is like my top two is like. And you can't tell if my voice is kind of going down the slope, but I just still feel like.
Which will be everyone's favorite, I'm sure. So, I'm sorry, was there a question? Do we have to do what?
So we have to.
It should already be on the computers. If not, then we'll make sure they get on there. And plus should be on the computers in this lab here. Okay, but we'll worry about that next week. So just as way of the class, remember that your assignment 4 is due next week. Hopefully you had a chance to kind of start on that already. Everything you needed was covered last class. Today may be helpful in terms of just kind of emphasizing what we learned last week. I mean, obviously, we're going to talk about more than 2 categories when it comes to the digit regression. A lot of principles are the same, so maybe that's helpful. But be working on that as well, so you can get in a draft to get some comments back on. I do have your assignment 3 drafts for you today. Make sure that I don't forget to give that to you at the end of the class. Just remind me to take the right track. And then I did grade the exam, so those have been posted as well. So I think that's all I got for you. Yes, it was busy, but it was good. Obviously, the holiday, Easter holiday is busy. Chaplain, but also pastoral work as well. So but it was good. And lots of fun with kids. They did Easter egg hunts. You know, hit all the eggs out in the front yard, and just like every year, someone ended up in tears. It's inevitable. So no matter how hard you try to make it fair, someone always ends up with more eggs, and someone's in tears. So that's the way it goes. So, but other than that, it was a good time. All right, let's see. So I guess I haven't posted I haven't put up because we're just trying to get the camera up and going. I didn't open up a PowerPoint yet, so give me a minute. We'll get that up here in a second. You'll notice that there is a PowerPoint and a data set file. Data set file will look very familiar, except this time it'll have all categories of grades, not just A's and B's. Oh, and then worksheet number 9, what I'd like to do is go find an actual article that uses logistic regression, whether it's dichotomous or multinomial or ordinal, doesn't matter, and answer some questions related to that article. So should be a good exercise to kind of tie together what we're learning in class to what's actually published out there. All right, the good thing is that most of what we talk about today is going to be very familiar to last week. There's multiple categories, some differences in interpretation, some things you look out for, like alpha inflation, you're making multiple comparisons, stuff like that. We'll talk about those. And that how we talk about the ordinal outcomes is slightly different. And when we look at our comparisons, we'll talk about that as well. But otherwise, it should feel very familiar to last week. When you look at the output, same type of thing. You got an overall model, and you have your goodness of fit, and you get individual predictors. You have multiple constants, but generally it'll look very similar to last week. All right, so multinomial and ordinal outcomes. So what we're really saying here, we have more than 2 categories in our outcome variable. Very similar again to binary logistic regression. If it's categorical, right, then we should be doing the multinomial. If it's an ordinal outcome, then we should be doing ordinal logistic regression. Still going to interpret it in terms of the natural log of the odd ratios. That doesn't change, but now we're going to have multiple comparisons, so 2 at a time. Right, and so when we make those comparisons, because there's multiple comparisons, we do have to account for alpha inflation. So do need to keep track of how many comparisons we're making and try to adjust our alpha level to those number of comparisons. Each comparison would be in terms of some reference group. So you get to decide which group will be the group that you'll compare all the other groups to. So we call that the reference group. And whether you're doing ordinal or if you're doing multinomial, you get to decide what that reference group is. It's actually pretty easy to change that reference group in the analysis itself. Okay, so with binary logistic regression, there's always only one comparison because you only had 2 groups, right? So you're going to have multiple comparisons. The model is the same, so nothing new there. Again, if we apply the base E through both sides of the equation, we still get odds to the exponents of that base E. Again, in your output, this is what's reported as your coefficients, right, with the base E. So that we have to turn that into an odds ratio. For binary logistic regression, it gave it to us automatically. For the ordinal, we'll actually have to calculate it. But the formula is essentially the base of it is still the same, not any different from last week. Assumptions are also going to be similar, still need independence of our observations. So in other words, we want to be careful if we're collecting data all from like one class or from one family. We've talked about that before. Still want independence of our predictors. In other words, no multicollinearity. So if you were to fit a ordinal logistic regression or a multinomial logistic regression, you still want to check for collinearity among your predictors. I still want to look for any influential observations. And of course, you are using categorical data, so you're losing statistical power. So you want larger sample sizes than you would have if your outcome was a continuous variable. So all those things still apply. The only thing new that is up here that from last week is this last one, is that the probability of any particular outcome group should stay the same across all levels of a predictor. We call this the independence of irrelevant alternatives. Essentially what we're saying there is if I have an outcome, let's say that's 4 categories, right? And I have some predictors. Those predictors should give me the probabilities of being in any, for a participant in any one of those categories. Some percent chance, some probability, right? If I was to, for some reason, remove one of those categories, those probabilities should still stay the same for the other 3 categories. Because it's a nominal variable, right? Because it's a nominal variable, it shouldn't be impacted, it should be independent of the other groups. So it shouldn't be affected, like it probably should be affected. Categories, refit it, probability should stay the same for the other 3 categories. Things like the coefficients should be stable. Think about with multicollinearity, the coefficients not being stable, they change from model to model. That's kind of the idea. So here we're removing a category of the outcome. These coefficients. There is no statistical test for that. And so there's always some fluctuation, but there's no like standard of what is too much. Just realize that if you were to remove one of the categories of the outcome, the probability of the other outcome should still remain the same, given any predictor or set of predictors. But that's the only additional assumption to this particular model. All the rest you already know and love from last week. Ready to jump into an example? Get right into it. Yeah. Get warmed up with an example. It's like rubbing your hands near a fire. Get warmed up here. Okay, so let's do. Let's look at student letter grade here. So obviously A, B, C, D, F are not completely independent of each other. That is on an ordinal level scale. We would consider like A being higher than a B, and then a C, then a D, then an F, so on and so forth. So ordinal logistic regression are probably best here. However, if we wanted to treat this as I want to compare like A students to C students, or D students to A students, or C students to B students, or whatever it may be, we could treat it as a multinomial logistic regression. So again, it kind of comes down to the purpose. What is the research question you want to answer? Do you want to compare A students to C students, or do you want to compare A students to all other grades, or AB to all other grades, or AC to E and Fs, whatever it may be. So collectively in ordinal fashion, right? So we couldn't do like A and B compared to the rest, but I could do AB and do a split here, or do a split here. Right? That's the case of ordinal regression. If I want to compare any 2 to each other, then a multinomial regression. But just realize, just because it is letter grade, it's not a truly nominal variable. It is an ordinal variable, but there's still some use in applying the multinomial logistic regression, even if you have ordinal data. And sometimes it's actually easier to interpret and make some useful statements from. Okay, so in this particular case, here's our research question. Does the quality of textbook reading, we'll go back to that, differentiate among student letter grades, not just A, B students, but all students, regardless of the grades that they have. We know it does for A, B students. We saw that last week. What about C, D, and F students in addition to that? All right, so we can go to our SPSS output here. I'm sorry, data file. Sorry, I'm still warming up. All right, and you'll see that we have our letter grade here. These letter grades are in terms of a 0 being an F, a 4 being an A. So think of it as a GPA scale, right? 4.0 is A, so on and so forth. You get, if you have a B, you get 3, C's, you get 2, so on and so forth. So that's how it's being coded there. And then we have lecture absences, reading quality, employment as all possible predictors of letter grade. I think in this case, we want to look at reading quality of the textbook first, because that's what we looked at last week. And now we're just going to look at all of our letter grade categories. All right, so to calculate our ordinal logistic regression, we're going to analyze. We will go down to regression. And like I said, I think we have plenty of time today. So if you have questions, by all means, ask them. We do have 4 examples, but I think they'll go fairly quickly. Those are all very similar. From there, you'll go down to ordinal, right? Surprise, right? So ordinal outcome, we'll go down to our ordinal regression. Click on it. Really not a whole lot to do here. Our dependent variable is going to be letter grade. We're trying to predict the type of student we have as far as their letter grade. And in this case, we're going to use reading quality. But the thing you need to remember here is that you want to put this in the covariate box. And the reason for that is if you put it in the factor box, and you can test it, you can see what your output looks like. If you put it in the factor box, it's going to look at every level of your predictor to every level of the output. And so in this case, because reading quality was average over a couple of administrations, then I think we got to like 4.5s and 3.5s. So there's like 8 different categories. Then you got 5 different letter grades. And so 8 times 5 is 40 sets of output on a lot of stuff that you don't care about, right? And so we put it in a factor, it's going to give you all possible combinations of the values. You can imagine the nightmare would be if you had a true continuous variable where all of your continuous variables are, you might have a couple that duplicate or something like that. You just have a string output. So just make sure you put it into your covariate box. You'll quickly realize you make a mistake. You put in the other one because you're gonna get a lot of output. You're like, this looks like a mess. And then you remember, oh yeah, that's right. I'm supposed to put in my covariate box. So put it in there. Again, if you want to compare the two, feel free to do that. You can look at them. You'll see you'll get a whole lot more output if you put it in as a factor, because it is going to try to create a regression equation for every possible combination, even though that is not what you're interested in here. I don't think we do a whole lot over here. I'm just going to go through these just really quick. If you wanted to get like your predicted category, or you want to get the predicted probability, you could check those and it would create columns in your data tab for those categories, predicted categories and predicted probability. It's interesting to look at, but it's not particularly useful. I mean, I guess if you're looking to try to predict little Timmy as an individual and his probability of getting an A or B, that might make sense. But if you're just generally interested in the variables and if they're related, then it's not useful to you. Okay, so nothing there. And we don't need the rest of these. We'll just double check really quick. Yeah, we're good. Okay, so we should be it. So we good. So nothing else really to do here. Like I said, if you were interested at the individual participant level, you could save some of the probabilities and categorization, but we don't really need to here. So let's click OK. All right, and that is going to be your output. You'll see the first box there is just giving you the percentages and counts. So in this case, 164 A's, 207 B's, only 29 F's, right? It gives you the relative percentages. So just a summary of your data. Again, no means or standard deviations here because your outcome is not a continuous variable. So counts and percentages make sense. As a reminder, we do sacrifice number 3 in this class. So this is just your output printed out. So again, if you want to take notes on it, I know a lot of you do it electronically, that's perfectly fine as well. Obviously, whatever works best for you. So let's take a look at some of our output here. Okay, so first thing that we can look at the overall model. This is that model fitting information. This is very similar to what we did last week. So just overall, is the model significant given the number of predictors that we have? We only have one predictor here, so two variables, right? Two parameters, so we're going to have 1 degree of freedom. And then we have our chi-square value. Again, if we wanted to report, we would report this chi-square value for the overall model. And then we have our significance level. And so we would say in this case, does it look like reading quality matters to student grades? Yeah, whether classified as A, B, C, D, or F. It does look like it. Probably not too surprising given what we saw last week and what we've seen, or what we would think anyway, right? If you read better, your textbook better, you should get better grades. All right, so now we have our goodness of fit test down here. And again, what we're looking for is this particular, are the expected predicted values, the expected values, which are predicted values, are they matching our observed values? In other words, when we use the regression equation to predict the grade of each of these observations, how well is it doing to the actual grade? And in this case, we see that we have some significant values of 0.424 and 0.296. And so what would you say? What would you say here? Correct. Yeah, because the null hypothesis here is that there's no difference between what is predicted versus what is observed. So we do not want this to be significant, right? And that appears to be the case here. So so that looks good here. We then have our R squared value down here. Cox and Snell, Nagelkirky, and McFadden. So help me out here. Which one would we want to use and why? We have 3 up there. Which one would be best? Bobby, Cox, and Snell because
Greater than 0.75 or that second one. Underestimate.
Yeah, underestimate. So McFadden underestimate. So that pseudo R squared value of 0.02 is like an underestimate. Cox Snell is a better estimate, but remember it cannot reach a value of 1. So larger R squared values end up getting truncated, right? So so the Nagelkirky adjusts for that, but really doesn't make a really big impact until you have a very high R squared value. So you notice here that they're very comparable to each other, 0.056, 0.059, because we have a small R squared value here. So it's not making much of an adjustment for it. So the Cox and Snell, mathematically, this value could never reach 1, right? And so if we're thinking about R squared, traditionally, we're thinking about the percent of variation accounted for. That if I had a perfectly predicted model, I should account for 100% of the variation in the outcome, right? So if it's a perfect prediction. Now, when it comes to Cox and Snell, if I have a perfectly predicting independent variable or predictor variable, then we would expect this value to be 1. But the Cox and Snell, because of the math in it, can never reach 1. And so it'll never match the true value that should, if that makes any sense. And so the Nagelkirky tries to adjust for that. So no, it hits a ceiling that's less than 1 or 100%, right? And so that's problematic, obviously, if you have high values. So Nagelkirky tries to adjust for that. Nagelkirky will reach a value of 1, in other words, 100% when it comes to that model fit. And so it is a better estimate at higher values of R squared. Lower values, it tends to overestimate a little bit. Yeah, and usually we're not using Nagelkirky because rarely do we have in the human sciences have predictors that are predicting 60% or 70% or 80% of the variance. That's actually really, really rare. You might see that in like engineering,
You might see that in maybe some medical studies, but generally what we do, we're not going to see R squared values that high, and so Cox's smell will be just fine for us. Oh, yes. So lower,
I think what I said, I don't remember exactly, but I think I was saying at lower values of R squared, Nickel Turkey tends to overestimate. Is that what you're asking about? Yeah, but it doesn't overestimate our flash, they're really similar, right? So
again, at high values of R squared, the Cox's smell will underestimate. The Nago-Kirky will be better in those situations. All right, let's look at our parameter estimates because this is going to look a little bit different. So we should talk about the interpretation here. So you're going to note here this threshold. So really a threshold is like that point in which you reach the next level in this ordinal variable. The threshold when the probability is now more likely to be a D than an F, or more likely to be a B than a C, right? So that's what I mean by that threshold. Think of this as the constant, right? Essentially, you have a constant, but it's for every level of your ordinal outcome variable. All right, so 0, 1, 2, 3, 4, or F, D, C, B, A, right? Well, there's no A up here because A is our reference group. But just note here that it's basically setting that baseline constant to which you would add, right, your coefficient for the slope in this particular case, your regression coefficient. Not technically a slope, but your regression coefficient. So your predictor is still down here. There's only one row for it, but realize that when it comes to the letter grade that you are using in your outcome, right, that it's going to have a different base or a different constant. I didn't say base, but a different constant in that equation. So you have 4 different equations where each of these thresholds essentially is serving as a constant. As you can imagine, as you get closer to an A grade, that value is higher. The further away, it is lower because it's a lot harder to go from an F to an A than, let's say, a B to an A. Right? And remember that a estimate of 0 for an exponent of base E is essentially 50-50. Right, and so that's why we see a negative, we see positive, because that point of 50-50 is considered a 0 in your estimates. Yes.
In the process of checking to make the reference group.
Yeah, let's go back and look at that. I can't remember. I think there was something like, you can select as being the highest value or the lowest value because it's ordinal, but let's just double check. There isn't, is there? Yeah, so with multinomial, there definitely is. You can change it. Here, you'd have to code it differently. So here, it's coding your highest value as your reference group. Let me just look at options just really quick. Yeah, I don't think I've noticed that before, but I don't see where you can change it other than in how you code the variable yourself. So it's using the highest value as your reference group. Excellent question. Not one I've looked at before. Multinomial, definitely you can change it. And I'll show you that too. Okay, so generally not so much interested in the thresholds. We are interested though in the coefficient for our prediction equation. You're going to notice here that it does not give you a conversion for the odds ratio. So you have to do that yourself. And you can just break out your handy dandy scientific calculator. You can also pull it up online as well. So we have them on the computer. But here we just put in our value of 0.37. Again, we want this e to the x because we want base e. So notice I got to hit my shift button on my calculator, and then I'll press my natural log button, and I'm going to get 1.45, I guess, 1.45. Indicating 1.45 times as likely for every one increase in reading quality a student is 1.45 times as likely to get an A grade.
Where did you get the coefficient?
Right here. Oh, I'm sorry. I'm like pointing it on my screen, but you can't see it. Let me switch over. 0.37 is your coefficient, your estimate right here. So your regression coefficient.
So that 0.37 is only for A grade, because it's our reference group.
Because that's our reference group. Absolutely correct. So we said, in this case, it set the highest value as our reference group because it's ordinal. So it's got to be the highest or the lowest, right? So we can't pick anywhere in between because we're saying that this is an ordinal variable where rank matters, right? And so we can't pick something in the middle to be the reference group. That would be a multinomial regression because they're all technically supposed to be independent or arbitrary of each other. So that's not the case here. So it can only be your lowest value or your highest value, again, how you code it. So if you wanted to compare to S, then just switch your code, reverse code it. Then a hand, Emily, or,
Yes.
okay.
Will you repeat the interpretation?
Yeah, actually, I put it in the slide.
Oh,
I think it's, which slide is it? Right here. So we'll come back to the other slides. So again, just notice that it's comparing B and below versus A, or you could A, B versus C and below, again, because of the ordinal nature of our outcome. All right, so other than A, so for every one increase in reading quality rating, students are 1.447 times more likely to get an A grade. You can see all the interpretation there that you would put in your output as well. Sorry, Austin, yes.
So I know you just said that the letter grades in there, like between whether or not this has to do with the sex relationship between the two. Does that mean that in the instances that we have ordinal predictors that we never need this or allocate independence of alternatives?
Say that again. We need never.
Well, if you're saying that if there's some relationship.
Oh, yes, because they're ranked data, like order matters, right?
Yeah.
Yeah, so the independence of relevant assumptions, I should have specified this applies for both. The categories are arbitrary.
And in the instance that we don't need that assumption, we know that they are.
Sorry, yeah, and technically, I haven't tested this, but maybe that works for ordinal. I don't actually haven't tested myself. If I was to erase one of the categories, would we still get the same rough estimates? Maybe, right? If that's the case, then maybe we can do that as well. And I know it's definitely for the case of ordinal outcome, I'm sorry, nominal outcome, because the labels that you give the values that assign to the category. So it definitely applies there. I'd have to look into see if it applies to ordinal logistic regression. Oh, that's a good question, though. Not one I thought about.
Come from the calculation, right?
Correct. Yes. So I'll show you again just really quick. So again, you're just taking your estimate, your coefficient estimate of 0.37, and then taking it to that base E. Yeah, 1.47. Yes.
in the equation slash statistics listed after the interpretation, why is the chi-squared slash x-squared to the wall? What is that?
It's a walled chi-square. It's a specific chi-square. So you have different chi-squares, like you have different F statistics, like a Levine's F or something like that. And so this is specifically a walled chi-square. So it's just identifying the type of chi-square you have. Let's see, just go back a couple slides just really quick. There's a couple things I definitely want to point out. So again, notice here that just for the overall model, students' reading quality of textbook was a significant predictor of students' course letter grades. We don't really get into how much it is until we get to the individual parameter estimates, but that would be the overall writing up for a model. When you are reporting, you want to include the beta coefficient. You want to include the wall statistic, probability of your test statistic. Remember, we do have to adjust for Bonferroni as well. So we need to think about that. And then, of course, our interpretation of the coefficient. which if we're looking here, our p-value is less than 0.001. So even if we were to adjust for alpha inflation, if we have 4 different comparisons, A to B, A to C, A to D, A to E, F, whatever, right? I said E, F. Right, so then we're gonna have 4 different comparisons, so we should be taking that alpha and dividing by 4. Right, and so really we should be comparing to an alpha of 0.0125. In this case, it beats that anyway, and so it doesn't really particularly matter when we're looking at our significance. But just remember that we do have multiple comparisons here. We have multiple equations, so we need to be thinking about inflation of the alpha. Another reason why you don't want to put your predictor into the factor box, because then you're going to get, like I said, 40 different outputs, and then you need to be thinking about alpha inflation on 40 comparisons, which would really reduce your alpha to adjust for that inflation. So just keep that in mind. Okay, so let me go back. Let me put this back up here just really quick. You have this in front of you as well, but you have your threshold, and then you have your predictor coefficient there. Right, and so it makes sense that if we were to go from like an F to an A, we have to go a very long distance, right, to get there. And that's why this the estimate for the threshold is so much lower than for an F than it is for a B. But if we were to write out these equations, right, I'll write a couple out and then I'll just show you. That might be easier. For that first one, it would be E to the threshold of 2.152. So again, a letter grade of B to an A plus 0.37 times the reading quality. If that makes sense, right? So for every unit increase in your reading quality, you're adding 0.37 to that particular base. Now, if you had something like, let's see, what's the one? One is a D, right? So let's put up an equation for that one. It would be E to the negative 0.811 plus 0.37 to X. So remember the probability, if I'm using this to predict for a single student, the probability from going from here to just 50-50, right, would be going from a negative 0.81 to a 0. Right, and so we'd almost have to move 2.5 places on my reading quality to get this to 0, if that makes sense. And that would give me a 50-50 chance of getting an A. Right, and so just notice that the distance from a D grade to an A grade makes it harder to get go from that D to an A grade just by increasing reading quality. So the only point I'm trying to make here is that your equation is going to be different depending on the level of that outcome variable. And so you're going to have 4 different equations here, all in comparison to your reference root of getting an A grade or increasing your probability of getting an A grade. Drew, yes.
So if we check up the predicted category probability, that's what we found. You know, when we did analyze regression or
Correct. Yes. Yeah. So you would get the predicted probability in that particular column. We can look at that if you like, and see like, okay, for this person, what would be our prediction for their particular grade given their reading quality? This is for 3, I think, right? Category has a 3. So just realize there's a different equation for every level of that particular outcome. Predicted, right? or even predicted category, we can look at that, continue. Okay, and now when we go to our page, we see that here, as far as what the predicted probability is, but then also here the predicted category. So in this case, this first person had a letter grade of 4, which is an A, but it was predicted based on this equation to be a B, based on that probability level. So on and so forth, B to B. So again, this is what we're comparing the predicted versus the observed, right? And this is where we get that that goodness of fit test, right? How well do our predictions match what the actual letter grade is?
Is it significantly different? You know, it's not doing a good job.
Oh, remember here, it is doing a good job because it's not significant, right? So remember our output here, go back there. That fitness test right here, it's not significant because there's no difference between, no statistical difference between what is predicted versus what is actually observed. So overall model is significant. How well does it fit in this prediction? It looks like it does a pretty good fit as well. But that's what it's comparing, predicted versus observed. Again, unless you care about the individual participant, it's probably not important to have those values, but it's kind of fun to look at, right? How well did it predict?
So actually, significance tells us how good the job it does. Doing the probability comparison, what we just did.
Yeah.
Give us the actual looking visual.
Yeah, I think I understand what you're saying. I'm not sure, but you're talking about what's in the, what we just checked and got in our, back in our, yeah,
You
so
see, okay, this is what
using the
predicted by this
equation,
observed.
right. This is what we predict versus what is actually observed. Yeah. Let's remove those really quick. Okay, there's not much else to it. But just look at the wording. Again, we're not so much concerned about the thresholds. That's just a starting point, right? What we are more concerned about is an interpretation of the coefficient for the predictor. Essentially what we're saying, for every one increase in reading quality, the likelihood of students getting an A grade increases by 1.45 times, right? That's really the interpretation we would go with when it comes to a write-up. We didn't talk about the pseudo R-squared. So same interpretation, right? So 5.6% improvement in fit when predicting student course grades when reading quality is entered into the model. And again, as a 5.6% given the baseline. It doesn't report a baseline in your output here like it does for binary logistic regression, but there is a baseline fit that once you add in that predictor, do we do a better job at predicting? In this case, looks like it does. So what size of effect would this be? Is it a small, moderate, large effect? What would you say here? Do you remember what the conventions are for categorical data? I'm writing them down here and then we'll see how close you get.
I think it's small. That's what I guess.
Okay, let's put some numbers out there. So what's a no effect? 0, R squared of 0 would be no effect, right? Yeah. Okay, what's a small effect for R squared?
Oh, because we lose
Remember,
statistical power, it has to be a little bit greater than continuous, right?
or a little bit less. You get the opposite direction, yeah. Because we're losing power, right? So,
I think it's 0.4, right?
I'm sorry?
1 point-
And remember the squared values too. Decimal squared becomes smaller. Yeah, you have it in your chart. That's true too. But honestly, like these are things that you probably should know whenever you're reading an article. Like, is this effect size small, moderate, or large? Just by reading an article, it should have these committed to memory for Cohen's D, for R, and for R squared. I would say that's something that, and of course, you know, the average reliability equation, you should know that. So what do we got? Throw some numbers out there. I got time. 0.01. Yeah, that sounds pretty good. That's a small effect for sure. All right, what about moderate?
0.06.
Yeah, okay, 0.06. All right, and then large. Someone said it. 0.14, right? Yeah. So again, you know, have those in your memory whenever you're reading an article so that you get an idea, like, is this impacting an individual person? So if I get a 5.6% again, if we turn these percents, that's 1%, 6%, 14%. This is a moderate effect. So not only is reading quality statistically significant collectively, it is also looks like practically meaningful for the individual student. If an individual student was to increase the reading quality that they use, that they're going to get better grades. Correlationally speaking, of course, but that would be the idea. Okay, so 5.6% is a moderate effect that's impacting individual as well as a group level. Okay, so this next part, these next few slides, I just put in here because I noticed with some of the the assignments, that when you get to that conclusion part, a lot of times it's like restating the findings, or it's not addressing the predictors. And so I thought these next few slides might be helpful when it comes to writing up an interpretation section, a discussion section. And I know we've talked about it before, but I don't think we've put up examples, so I kind of put that up here. All right, so overall, right? So if you're getting into a conclusion section, you would want to state what you found. So overall, we found that reading quality differentiates among student letter grades. That was our overall finding. And so now we want to get into that interpretation part. So assuming, right? So this part is assuming that your finding is correct. You always start off assuming your finding is correct. Now, it's easy when you do find statistical significance, right? Because you already thought about it. You've already looked up the literature. You already kind of know what to talk about. You can refer back to introduction, whatever it may be. Always much harder when you fail to reject a null, when you don't find what you were expecting to find. And so our automatic process is, I didn't find what I was supposed to find, therefore I must have did something wrong, and we go directly to limitations, right? But remember that interpretation, that first part is, let's first assume what we have is correct, right? And let's explain why. It wasn't what I thought it was going to be, but let me explain why it might still be a true finding, right, in the population. You can always later on talk about your limitations. So I think that's kind of hard for students, which also I think is hard for the discipline, right? When you think about it, we get into publication, and things that get published are things that are found technically, usually, right, generally statistically significant. So that once they get findings, they put in a file for, right, a file for a problem that we have, right? And so sometimes, just by the nature of what gets published, there are instances where a relationship between two variables gets published over and over again. It's all because of chance, and that all the true findings in the population are being suppressed and put into the file because there is no statistical significance. Right? And so, so don't automatically think that if you didn't find what you were expecting to find, that you did something wrong. Right? You can start off assuming you did something right, and then later discount, like look at your methods and stuff like that. But start off your conclusion, assuming what you found is correct. With plenty of space for the limitations later. Right. So in other words, we can sometimes get bad research perpetuating itself because we're only publishing statistically significant results, and those null findings don't get out there to compete with what is being published. Okay, so why do you think reading quality differentiates between grades, right? Our founding was that it differentiates among student letter grades. We can say, well, students with higher reading quality are more likely to think about the concepts, how they relate, which results in deeper processing of the material, which is going to increase their chances of recall when it comes to exams. So that's an explanation of my particular finding. Sometimes I'll see also just a restatement of the finding, but no real thought into, well, why does this exist, right? That qualitative piece that even though we didn't do a qualitative study, we still can think about, right, and articulate in some way of why this relationship exists. So again, once you have a finding, why does the relationship exist? If you don't have it, then why didn't you find it, right? In a way that you believe what you did was correct. All right, you can always talk about additional variables later. That's going to lead into limitations, right? Certainly students' attendance at lectures will matter. Oh, I think I added this. This should have been later. I guess I moved this up. So if we were to look at lecture attendance as well, right, and that was found to be significant, we can give an interpretation for that as well. So students with more lecture attendance are more likely to hear explanations. That's going to help them, with difficult topics will help them on exams, etc. So I guess I gave a second example too. My apologies. All right, so then you get into your limitations. So your limitations where you assume your finding is incorrect, right? And so again, this is easy if you don't reject your null hypothesis, right? It's easy to find like, oh, I didn't have a large enough sample size, or maybe it was the population or the sample I was using that wasn't representative of the population. That's pretty easy. This becomes harder when you do find what you expected to find, right? Because now you automatically assume that is correct because you found what you expected, that confirmation bias. And so you still have to wrap your mind around, okay, so let's assume for a second that in this particular case, we found that reading quality, right, is significant. Well, why might that not be true, right? So what if this finding is incorrect? Why might that be? Right, and that's what that limitation section is talking about. So whatever you put as a limitation should theoretically, if addressed, change the finding of your study. So going from statistically significant to non-significant, or non-significant to significant, or a small effect to a moderate effect, or a moderate effect down to a small effect, right? Some sort of change in how you interpret the outcome. All right, so so categorization of grades decreases important variability within letter grade categories. What we're saying here is restriction of range, right? So that's a limitation of the study. So if I'm going to say it's a limitation, I have to articulate why it would change my finding. And so using letter grades instead of grade percentages may reduce the validity of the findings, while reading quality may differentiate among letter grades, may not differentiate within letter grades. As a result, reading quality may not be related to grade percentage level. If we were to measure not by A, B, C, D, E, F, sorry, I don't know why I want to say E. That's the alphabet. For whatever reason, we skip E. But rather if we did percentages, right? 80% versus 72% versus 75%, right? So, can reading quality differentiate between someone who's getting a 70% and a 75% or within a letter grade? Maybe not, right? We've got to articulate that limitation if we truly believe it's a limitation. So if reading quality was significant before, then here we say it may not be related or not be significant if we account for that variation within the letter grades. So that's how our explanation should be, right? So again, thinking that my findings are incorrect. Yes, Austin, I think I didn't see. Okay. Yes, Susan.
I'm sorry, I'm just trying, I'm finding it a little bit difficult to understand that reading quality may differentiate on non-letter grades, but not within.
Right, exactly. So can reading quality differentiate between students who get like a 72 and a 76 or a 72 and a 75? They're all seen as C's, right? But will reading quality differentiate within that particular category of C's, right? Maybe between like a 70 and like a 79. What about between, two percentages closer together? Maybe not, right? Maybe it does. I don't know, but it might be. So anyway, just realize again, interpretation is assuming your findings are correct no matter what they are. Limitations is assuming your findings are incorrect and your interpretation of that analysis would change.
I'm sorry, one more question.
Yes.
You said that when you work on this for the individual units role, that you do not find any differences. But it's saying that reading quality will differentiate among categories.
I'm sorry, say that again.
So initially at the beginning, you mentioned that you work on this for an organization, was you find out?
Yeah, it's for like, McGraw-Hill.
Yeah, so I was wondering that if you actually know, if you really quality differentiate among letter grades, then does that mean that whatever they were doing actually impacted the letter grades for the students?
So whatever they're doing naturally would impact their grades. I'm not sure I'm following.
Sure, that's good.
Like, is there any variables?
Yeah, that always could be, right? I mean, whenever you have results that are not consistent, it could be, could be an interaction, it could be confounding variables, whatever it may be.
Or like maybe there's something about students who get higher grades than others. Maybe they
Well, yeah, I mean, those who, I mean, like conscientiousness, right? So students who get higher grades tend to study more, tend to read their books more. Is it really because they're reading their books more, or just because they're high performers and conscientious, right? So it's other possible explanations. Again, that could be a limitation too that you could talk about. All right, so the point is that when you get in there, just make sure you're explaining what you're finding related to the predictors that you are actually measuring. And you'll do a little bit better in that conclusion section, and particularly when you go to publish something as well. Oh, I'm sorry. Yes, this back row, because it's out of my field of vision. Jamie, yes.
I have a question from like 4 slides ago.
Sure.
Do you remember the R squared, the pseudo R squared, and you wrote constants down? Do we have to do that?
You should, and yeah, so if you're publishing, you should, because there's so many different pseudo R squared, the natural question is going to be which one did you use, right? Because there's a big difference between McFadden and Cox and Snell. McFadden's a small effect. Cox and Snell is a moderate effect, right? And so, yeah, I think you want to specify that as a subscript. You're welcome. Good question. Okay, so let's treat this as categories rather than an ordinal variable. So let's treat it as a nominal variable when it comes to letter grades. What's nice about this is that you can actually compare different letter grades to each other. A to B, B to C, D to A, right? So it doesn't have to be in a particular order like it does with an ordinal logistic regression. That does give you some advantages. Again, there's always a trade-off. The disadvantage of taking an ordinal variable and treating it as nominal is you do lose some statistical power in that process, right? And so, so there's always a trade-off, but you can make more meaningful comparisons. If I wanted to compare students who are predicted to get A versus those who are predicted to get, let's say, a C, we can make those comparisons if we treat it as a nominal rather than an ordinal variable. Again, with the minor loss of power. Okay, so again, we'll still stick with reading and we'll still look at letter grades, but now we're going to do it as a multinomial logistic regression. Again, we want to make sure we're addressing alpha inflation. And so we still have our letter grades, 0 still in F, 4 still in A. We'll start with making A grade the reference group, but I'll show you where you can change that as well. Okay, and then reading quality is still the same scale. So let's go to our data. We'll go to analyze regression. Now we're going, there we go, regression, stop it, there we go. And now we're going to go down to multinomial logistic. Same thing as before, we will put our letter grade in the dependent variable. Notice it says reference category. We can change that reference category. We'll identify here in a second. And then we're going to put our reading quality again in the covariate box. So again, we're not getting more equations than we care about. All right, so if you go to that reference category, you can choose the first category, you can choose the last category. So remember that ordinal was automatically choosing the highest value. So you can choose the first category, last, or you can custom, you can make it a C grade, right? Put a 3 in there or whatever it may be, or a 2 or whatever. And so in this case, we might put a 4 for our reference group. I'm sorry, say it again. No, it's right below it right here, this reference category. Under your dependent box. It should be under your dependent box there. All right, so we can put 4, and then we can just change it to whatever grade that it might be that we're interested in comparing to. So a lot more flexibility here. Again, that's why sometimes doing a multinomial logistic regression is better than an ordinal, because you have more control over those comparisons. All right, and continue. There is something that we need. It's not in the model, it's just statistics. Oh yeah, make sure you get your goodness of fit test. You can also get classification tables and stuff too. You can play with those if you want to, but we definitely need our goodness of fit test. So check that box. And I think that's all we need here. Just double check really quick. No, we're good there. If you wanted to save your probabilities or predicted categories, you could do that under the saved option or the save option. Again, sometimes need to look at, but not particularly useful unless you're trying to predict for a specific person.
Change the reference group to A.
Should be 4. Yeah, I put custom, put it as 4. So, but notice we can put any value in there, right? Anywhere from 0 to 4. Okay, and that's it. We'll click OK. Get our percentages again, and then we have our output.
So this example.
Yeah, no, I removed an example. It was kind of redundant. So I'm like, by the time we get through 4, you'll be sick of it anyway. All right, so we can go through again. We still have, so like I said, it's gonna start getting redundant here, right? So we still have our overall model, a model fitting information here. Yeah, not surprising. It's significant because our last one was significant, right? Our value chi-square has changed. Again, because we're using a different model now, but the overall still seems to be significant that the classification of letter grades can be predicted by reading quality. So we have our goodness of fit tests here, again, comparing what is predicted using the equation versus what is observed. And we're still saying it looks like a good fit because those are not significant, right? And then we have our pseudo R squared values down here. Not much different, a little bit higher for the R squared values, but still you're still same 3, Cox and Snell, Nagel-Kirky, McFadden. Cox and Snell, probably the one that we're going to go with here. A 0.063 is still a moderate effect, right? So that hasn't changed much at all. Not that I would expect to vary too much from our ordinal logistic regression, but there is some movement there as well. Austin, yes.
Wait, so why are we using Cox and Snell instead of
Same reason as last time. Do you remember?
Oh, in the last one?
Put you on the spot.
Yeah, you said that. Cox and Snell, push them, we can't reach one,
Correct.
so. Turkey. Controls for that.
Right. So it's going to be more accurate at higher values. So something up like a 0.7 or something like that. Here is 0.06, a very small value. Nagel-Kirky will tend to overestimate slightly, but it'll be more accurate the larger the R squared value gets. Here, we're only counting for 6% of the variation. So Cox and Snell is probably going to be our best bet. But if you reported Nagel-Kirky here, it's not that it's that much different, right? And you'd probably be fine. Just realize it tends to overestimate at lower values. Again, because of that adjustment, to make sure that it reaches 1, make sure it reaches 100%.
It's just you said it's also possible to get to like 0.7 in life sciences, right?
Yeah, if you get to like around 0.7, up there with your R squared, pseudo R squared, then you probably want to start reporting your Nagel-Kirky, because then Cox and Snell is going to start underestimating, and Nagel-Kirky will be a better estimate. So at high values, but again, like in our discipline, rarely we're going to reach those types of R squared values. Right, engineering does, but we don't.
And then there's a flip box.
Yeah.
Are we looking at both of those? or just one?
Yeah, you look at them collectively. There is a difference between the two. I don't remember off the top of my head. I can look that up, but I don't remember what the difference is between them. I want to say it has something to do with sample size, but I don't know if that's true. So I'm not going to share that rumor until I go back and refresh my memory. Yeah. So is it possible that one is significant and the other is not? Yeah, absolutely. That could be possible, right? And so then you want to look at, what makes them different from each other. I just unfortunately can't remember off the top of my head right now. I guess I should have prepared better for class. So I did my reading for class. I'm sorry, Susan, was that a question?
Yeah, finding out the hours and so I remember we did a calculation last week. But I also remember you showed us somewhere where we just say where I'm making calculations.
Yeah, so you're not given the information to do that calculation, this output. And that's why your McFadden's given to you there. The calculation that we got for that pseudo R squared is essentially a McFadden. And so it's underestimating it. You didn't get McFadden in the last output, I don't think. We did? But it should have been around what we calculated, if I remember correctly. So if not, then I gotta go back and look at it. So yeah, but you don't have the information here to do that R-squared, pseudo R-squared calculation. But even if you did, it would be an underestimate, and so we wouldn't use it anyway. Yeah, do you have that output from last week?
Yeah, I didn't have it done on the output, which calculated it.
Yeah, that's what, yeah, okay,
I thought
that's what it
about
was.
the last output today.
Oh, no, yeah, last week, I'm sorry.
Oh, okay. I was
Yeah,
like-
last week it didn't have it, and so we calculated it, and this week it gives it to us, but we don't have the information to actually calculate it here in the output. So which is great that it gives it to us, but we're not gonna use it anyway, so. But at least lose track. All right. Okay, so let's get down to our parameter estimates down here. Again, notice you're gonna have multiple categories. Each one's going to have an intercept. So it's not going to be called a threshold here because it's not ordinal, right? We're not going up a ladder. Think of like thresholds that I got to get to that next step. Right here is just comparing categories to each other, kind of like a closed talk test. As you can see. Right. And so in this particular case, our reference group is 4. So it's saying what is an F grade compared to an A grade, a D grade to an A, C to an A, B to an A, right? This is our reference group. So each of those comparisons will have its own intercept as well as its own coefficients. Right? These are all separate equations, again, which is why when we calculate alpha inflation, just like we did before, we have 4 separate equations here. If you were to then change your reference group to 3, right, and then refit the analysis, you're going to add additional comparisons, right? And so just realize if you did every possible comparison, you have to account for that, with your alpha inflation. So really go in thinking about what is it that I really want to know. Do I want to know A versus everything else? Do I want to know across all possible combinations? If so, you need to address your alpha inflation accordingly to the number of comparisons that you have. Yes.
Is that what we do when we put it in a factor box and I go variable?
Correct. Yeah, but it gives you, even then, it gives you more than you want to know. Yeah, I mean, just fit it in there because what you're going to get is every level of your predictor to every level of the outcome. So not only will you get the comparisons among the outcomes, you get every level of the predictors to the outcome. So like I said, if you have 8, like a 8-point scale, and you have five, great letter grades, you got 40 comparisons there. That's in the output, and more than what you really care for. So, but yes, it'll give you every possible comparison plus more that you don't want. So in other words, be thoughtful of your analysis before doing any logistic regressions to limit that output and also limit that reduction you have to do for that alpha inflation. So if all I cared about was A versus other grades, then I would have 4 different equations here. So I'd divide my alpha by 4. If I wanted every possible combination of letter grade compared to each other, we could use our formula. It's been a while since we've used it because it's been since we talked about ANOVA, but we can use our formula for the number of comparisons, which is K times K minus 1 divided by 2, where K is the number of groups. So if I have 5 letter grades, right, it's 5 times 4 divided by 2, which would give me 10 comparisons for all possible combinations of letter grades. Right, so to give you an idea, A versus B versus C versus D versus F, right? B versus C, D, and F, C versus D and F, D and F. Right, and that should be 10 if we're counting.
Can you do it with 2 6-sided dice? I'm just trying to figure it.
Can I do a 2 6-sided die?
Yeah.
I could. I don't know if I want to.
So that would be
Like 1, yeah, because you're done like 1 and then 1 through 6, right? 2 and then 1 through 6, right? So in that case, you have 36 different comparisons, 6 times 6. with 2 die, right? Here, like a B and A is redundant with A and B, and so
Yeah.
it's a little bit different.
Yeah, but those are-
Correct, yeah, so there's only 10 comparisons here instead of 20. That's why we divide by 2.
okay.
So, but anyway, if that's the case, if I had 10 comparisons comparing every possible letter grade in that outcome, then we need to reduce that alpha from 0.05 to 0.005. We divide it by the number of comparisons. So, but in this particular case, if we were just concerned about A grades compared to the other letter grades, we would be using a significance value of an alpha of 0.0125, and that's what we would use for our comparisons here. I think in this case, they all are still under that, right? But if we were to look at all possible combinations, it would have to be under 0.005, and we see that this one wouldn't make it, right? And the other ones I think still would, but not comparison wouldn't be significant. If we look at every possible comparison of letter grades. So the number of comparisons matter and how it impacts your Bonferroni correction, your alpha correction. Okay, so let's talk about it. So let's look at so we can look at, we already seen like A to B, right? We saw that with the binary logistic regression. But if we were to compare like a C to an A grade, would the extent of the textbook reading distinguish between A and C students? What would you say? Yes, it's significant, right? And it probably makes sense, right? The further you are from A, the more likely it would, right? And so generally speaking, but that's how we would look at that. So we're looking at B versus A and predicting C versus A grades or D versus A grades, so on and so forth.
So what is the interpretation for what's the main app? It really doesn't matter how well you read.
No, it does. It still matters, right? The degree to which you read your textbook, the quality of your textbook reading can differentiate between an A and an F student. But we would expect it would because they're so far apart, right? In fact, you can see that the coefficients tend to get larger or more extreme as you go down letter grades, which would make sense that the reading quality would have a tougher time distinguishing between A and B than it would between A and, let's say, D. What is interesting is that you get to A and F and it actually doesn't quite distinguish as well as, let's say, A and C and A and D.
I'm looking at the significance.
Sure, yeah, same thing. But your coefficient is related, again, to your standard error, but also to your error significance. Let's see here. Notice that you do get your odds ratio right here. So again, you don't get your odds ratio with the ordinal logistic regression, but you do get it here. Oh, we do employment as well. Okay, all right. I'll just look at my examples. Yes.
So when we're doing the interpretation for all of these, like in a paper, because they're all significant, we would just list them all with each.
I would put it all on the table and I would just go with an overall conclusion that it appears that reading quality distinguishes between A students and B, C, D, E, and F, and then C your table.
Okay.
Because that would be a lot to put in there. Unless you had a very specific comparison, that's really cool. Yes.
What would that APA table look like?
Drawn out for us.
Drawn out for you. Yeah, so yeah, that would be because your intercepts are different for every comparison, right? So usually what you end up seeing is just like A versus B, the odds ratio, A versus C, the odds ratio. You wouldn't put in the intercepts per se. You could do it, and I guess if you're trying to be very thorough, you would, but you don't generally see that in a logistic regression. You just see the odds ratio for those specific comparisons. Along with the confidence interval for it as well, because they're associated with that odds ratio. So I don't know if that was helpful. I don't think that was helpful, but
I'm asking,
but
plug it in place and play.
we would reduce it. We would reduce it to something like. Comparison. For your outcome, right? So A versus B, right? And you can still put in your B value coefficient. So if these are your columns, so put in your B value coefficient. You can even put your standard error in parentheses or separate. You put your T statistic, P, your odds ratio, 95% CI for your odds ratio, right? So it would look very similar to what you have there, but just notice we're not putting in the intercepts here. Whatever it may be, right? Because each one's going to have its own odds ratio. Again, if you wanted to be thorough, you could put in your, your intercept, put a column for intercept over here. But we wouldn't care if the intercept's significant or not.
So if we're pulling like individual interpretation by individual interpretation, you can't necessarily use the same interpretation that we use for the ordinal one, because not all the odds ratios are the same.
Correct. You do have to look at it. So again, which comparison are you particularly interested in? Now, for something like this, where you may have several different comparisons there, it's not worth your time to list it all out in the writing portion of your article. That's where you put it to a table and just go, what is my general conclusion? You can report your overall chi-square, right? And then you can always put in your table the individual comparisons. You don't usually have the word space in an article to talk about every single comparison. So unless there is certain ones that were you can use one or two as an example, or one or two that you find very compelling, but I wouldn't do any more than that. Yes, Jim.
Back to the table thing, when we're doing the assignments, and you have the, on the left-hand side where it says like A versus B or whatever you have written down, would that be like model 1, model 2, model 3?
Yeah, you could call them models, but I wouldn't even label it as a model. You could, because they're all different regression equations. You certainly could, right? But you can imagine that after like 20 of them, it gets kind of cumbersome. Right? So generally you don't see that in an article where it's like model 1, model 2, model 3. So, no, you just wouldn't put model. You wouldn't identify model on there at all. You would just give your odds ratios for all the comparisons. But generally you don't see it broken down. Now, if you have multiple predictors, one outcome, like do with like, just binary logistic regression, then yeah, you can put it by model, or regular multiple regression, you can do it by model. That makes sense. Here, there's just so many different comparisons that it just visually is not appealing. That makes sense. But realize that, for the sakes of this course, I'm not asking you to do a multinomial logistic regression or ordinal logistic regression. You're doing your binary logistic regression, right? And that simplifies your output a lot. I don't know, was that a question? No, okay. I thought so. I raised it. Okay, so let's fit one more just really quick. Let's change that reference group just so you can see what it looks like, how it changes the output. So again, multinomial. Let's change that reference category. Let's make it a C grade. Let's make it a 2. All right, and then we'll hit continue. Click OK. I'm just going to jump right down to those parameter estimates. All right, and then if we're looking at maybe 2 wasn't the best, but that's fine. That's okay. All right, and we're looking at those odds ratios. Notice that some are above 1, some are below 1, right? And so it doesn't change necessarily the overall finding for the comparison that we compared to. For like 4 versus 2, we're going to get the same output for, but now we have additional comparisons. So what a C is compared to a B, which you didn't have before, a C compared to a D, which we didn't have before. So changing that reference group does give you additional additional comparisons that you wouldn't have otherwise. So like between a C and a B, right? So our reference group is a C, and then remember 3 is a B. And so you look, is that significant? No, it isn't. It doesn't look like reading quality distinguishes between B and C students. It doesn't look like it distinguishes between C and D students, right? Or even C and F students. Yes.
So then, does the long-term expression the comparison that we had initially plus the additional?
We have to change that. Yeah, we have to adjust for the fact that we just added 3 new comparisons. All right, so now we have 7 comparisons. What we had in the last output plus this output. So now it's 0.05 divided by 7, right, for that significance. All right, but just note here that before A compared to all of the other letter grades were significant, but if I look at C compared to the other letter grades, right, C to B, C to D, C to F are not significant. Right, so reading quality does not seem to distinguish between, C and B, C and D, C and F, so on and so forth. Right. So again, to kind of get at that overall story, if you want to look at those comparisons, you can do that. Just the penalty, of course, is now adjusting for that alpha inflation. Divide by the number of comparisons that you have. We now increased it by 3 comparisons. Now we're using 7 comparisons. Okay. I don't know. I got 2 other examples here. Let's see. Let's do one. So I think I chose this next one because it gives us a different coefficient. Instead of being negative, I think it ends up being positive. So let's take a look at that really quick. I can't remember exactly what it was. But notice that oh no, it's because so note here that our predictor is now dichotomous as opposed to, so it's less continuous, right? It's now dichotomous. So let's see how that might change our output. So multinomial, still, let's take out reading quality. Let's put in employment. Let's change that reference category back to a 4. So back to that A grade. We should be good everywhere else. And we'll click OK. Okay, so you walk me through this one since we've been through it already. We'll start off with our overall model. Does employment seem to distinguish between letter grades? It looks like it. Notice that we don't have a goodness of fit test here. That has to do with the fact that our predictor is categorical. Mathematically, I'm not sure why that is, but I can always look into that. But do notice that we do get an R² value here. And so what would you say as far as the size of that effect? Yeah, it looks like it's getting closer to small here. So even though employment seems to differentiate collectively at the group level, probably very difficult to predict for any one student. Just because a student is working full-time or is working, so is working doesn't make it necessarily easier to predict for an individual student. Lots of students working versus not working seems to matter when it comes to distinguishing those grades. Okay, and so if we're looking at our different grades again, that first one is B versus an A. Does it seem like employment distinguishes between those 2 grades?
Maybe.
Yeah, no, maybe. It's on the fringe one. Is it though, right? Do we do our alpha adjustment, our Bonferroni adjustment for alpha inflation?
It's not.
Probably not, right? So again, our alpha here is not 0.05, it's 0.0125. So it doesn't look like employment is distinguishing between A and B students, right? Maybe between A and C students. Maybe or maybe not between A and D and A and F, right? It's right on the borderline. Now we're talking about like on the borderline, do I count this or not, right? Again, thinking of all the assumptions we may be violating. Yeah, so a little less clear here, right? And so just remember again, be thinking about that alpha inflation, the bond proning correction. Right? You know, are we making that adjustment?
So if we were looking for implementing some sort of programs to help support students, we would target maybe B and maybe just C students. See if they can use additional help or whatever, because they're and we need to get them today.
Yeah, so if you're looking at, you know, between those employed or unemployed, right? So if you're employed, you're gonna have your harder you get a better grade, right? So so that's where that distinction comes in. So you might be as an intervention targeting those who might be employed students, right? And then we might be looking at, well, what is the reading quality? Can we improve that? But if they're already B students, you know, it may not actually help them get to that A level. Does that make sense? Because that's not significant A. But if they're C students, maybe that helps them get up there to a higher grade of A grade. If we focus on their reading quality of the reading. This is for if we're trying to apply this.
Yes, and the intercept is 0.
Yeah, it doesn't quite, the interpretation isn't the same as it is with your regression. So remember, the intercept was the average of the zero group, right? So it's not our outcome in our regular category. So that would make sense. An average of it would make sense.
This value is.
So this is your prediction. Yeah, this is your predictor. So it's just all we're really saying here is as you go from employed to unemployed to employed, right? And so you're thinking that it's linear, right? So every one unit change, but it's not linear. Right? Yes, it's in separate groups, right? Yeah. So all it's really distinguishing is there a difference when it comes to this comparison between A and B students on whether or not they're employed or unemployed? So is there employment? Look at it more this way. Does employment matter when it comes to distinguishing between A and B students? I wouldn't break it down as going from 0 to 1 or going from unemployed to employed because it's not. You got to change how you think just a little bit because you're thinking in terms of like a linear regression and it's not really what it is. Yes.
Okay, so the interpretation slash the big take home message is, does employment matter in distinguishing between A and B students, A and C, whatever? Not between A and B, but the rest, yes.
Yeah, looks like it. Yes. Yeah. So employment seems to predict the classification of between like C and A students or between D and A students, but just not between B and A students.
So you're saying 0.16 is just close enough. Is that how you're making that decision?
Yeah. Yeah. I mean, I might consider that because that's really close, right? So again, you know, what we set that alpha is fairly arbitrary. I do want to control for alpha inflation, but I'm still going to be a little bit flexible as far as, you know, something that's really on the borderline. But I wouldn't be flexible with A versus B here. That's far enough away from 0.0125 that I wouldn't personally feel comfortable saying that it distinguishes between A and B students. I'm sorry, employment distinguishes between A and B students. Okay, I think you kind of get the idea here. The last example is looking at both of your predictors. Again, we're concerned about things like collinearity between your predictors. So we can fit that. But like I said, today's gonna be a pretty lax day. We're kind of just winding it down here. Let's look at that last one. And then if you have any additional questions, we can address it. But otherwise, that's all I'm going to have for you today. So notice we didn't take a break, but I anticipated us getting out a little earlier. So I kind of ran us through a break knowing that instead of come back for 20 minutes, let's just run it through, right? Okay, so we can put in our reading quality. We can also put employment. I guess we could put absences in too if we wanted to. Just fitting it one more time, but now with multiple predictors as opposed to just one. At this point, we've only been looking at one. So what happens if we put in two predictors? So both reading quality and employment. Again, we'll leave our reference category A here. We could change it again every time we do a new analysis. We got to adjust that alpha inflation. All right, let's click OK here and let's see how our equations change. I guess first of all, overall model, is it significant?
Yeah.
Yes. Notice your degrees of freedom here is 8 because you have multiple levels of your predictors for both your employment as well as reading quality. If you're looking at our prediction of the predicted versus absurd. I'm so tired. It's not even funny. Like on my mind right now, I'm thinking like in 3 weeks, not even 3 weeks, I'm gonna be gone for the entire summer, and I got so much to do before I leave. So I'm just like, so much to do.
I thought you said it's taking classes. Yeah.
I'm sorry?
I thought you said it's taking classes.
I'm doing training for the summer and I'm teaching, but I'll teach from distance. But I'll be gone from April 23rd to August, like right before classes, August 11th.
Where you going?
Barbados for a little bit.
What?
And then South
Amazing.
Carolina. So not as exciting.
That's dope.
I know, like, oh, you got to go training in Barbados. I'm like, oh, that's gonna be terrible. I don't know if I can handle that.
Don't forget to take pictures.
I don't want to take pictures of it. It's just me. I'm like,
Have fun.
okay, let's look at this last one here. I'm sure I'll enjoy myself. All right, so let's see. So a good as a fit looks good, right? It's not significant. That's what we want. Looking at our pseudo R squared with two predictors, we would expect that R squared value to increase, which it does. Still a moderate effect with our two predictors. All right, let's go down to our parameter estimates here. So notice here that we still only have 4 comparisons, right? Just because we added a predictor doesn't change the number of equations that we have here. There's just now 2 predictors per equation. So the question is, if we put them both together, I guess we should have looked at a correlation too to make sure they weren't highly correlated. We could do that in a second.
Oh, we're using Nagel for this time? Why not? It's like 0.08.
Like 70%.
Oh.
Yeah, we need.
Oh, I got so excited.
Sorry. You probably will not see naval perky in anything that you study. Sciences.
That is
Like,
confusing.
let's go. I understand a lot better.
Okay, so in this case, again, bond Ferroni correction, adjusting for alpha inflation, still 0.0125, right? Still only 4 equations, right? Only making 4 comparisons, A to B, A to C, A to D, A to F. So that doesn't change here. And so again, each one, for it to comparison, like does employment and reading quality distinguish between A and B students? What might you say here? So looking at this first comparison, A, which is our reference to B, does employment and reading quality distinguish between A and B students?
Yes.
Reading does, but it doesn't look like employment does, right? So again, think of this as separate regressions I've looked at before. We're still just looking at
right, just that right there, we still interpret the same way. So in this case, this does not seem to predict, but this does, or distinguish, this does, right? And so, at least between A and B students. A and C students, look like it's looking pretty close, right? So again, that's one of those borderline ones that you're gonna make that judgment based off of, you know, assumptions that are being made, et cetera. But certainly reading quality seems to, maybe not between A and the E students. So maybe not, that's kind of getting away from our adjusted alpha. Reading quality still seems to. So you can still get the idea, but again, we're treating each of these comparisons separately. Each with their own regression equation. Some cases, both your predictors may predict. In other cases, maybe only one. Other cases, maybe none. But you'll take it equation by equation.
Multi-collinearity, just for that, which we're about, if there's a connection between either a high or low quality of reading quality and whether or not people choose to be employed.
Right, so employment and reading quality, maybe, you know, are they related to each other? If they're highly related to each other, then again, our coefficients become unstable. So it's the same principle, those coefficients may be unstable, the errors, the standard errors may inflate, right, therefore impacting our test statistic. So we do want to check for collinearity. The same things apply here if our predictors are highly correlated with each other. And so we could just do a quick correlation here. There's only two of them, so bivariate works just fine here. And we can compare reading quality to employment. All right, and our correlation is a negative 0.068, not highly correlated at all. We're not really concerned about collinearity. We're probably not worried about instability of the coefficients here. So remember what value that is when we start to worry? Around 0.4, we start to worry about it. We are definitely concerned at 0.7 or above.
You're a great teacher.
I know, it's good. It makes me feel good when you guys remember. What's that? Yeah, it hurts my soul.
Oh.
No, you say that because I've been in meetings where I sat in with a student who's working on like their thesis or dissertation. And then I'm like, we've covered all of this. And I'm like, go back to your 70-50 notes. And then come back and we'll talk about it. I have done that. No, if it's like one or two questions, I'll just answer it. Like, we'll just remind you, whatever. But if it's like, this is like the 10th question that you've had that we've covered this time, I'm like, okay, go back, review your 70-50 and then come back and see me. So, yeah. And then at that point, I feel like, does anything I do really matter? I mean, I get paid, which is nice. I get that, but like, does it really matter? Yeah. But then I have students who, you know, who remember well, none of them remember everything, but they do better. So. All right. Anyway, collinearity doesn't seem to be a problem here, so we would be confident that these coefficients are fairly stable. All right. Like I said, today was going to be pretty straightforward considering what we covered last week. Covered a lot of the same things. We look at the output overall test, look at your goodness of fit, check your R-squared for the effect size, then look at your parameter estimates. It follows generally the same order. Just remember with ordinal logistic regression that it's not directly comparing your letter grades to each other, but rather their rank within the ordinal scale of whatever you're measuring. So that's the only real difference. So that's all I got for you. Sound good?
Yeah.
Okay, and then you can give a sigh of relief that everything from here on out is review with the exception of M+. Okay. So the content stuff will be very familiar.
Next week is next.
We'll start M+ next week.
Any test remain now? Any more tests remain? Any test we should take more. So we finish the test. Any test, any exam more?
We have an
Like test
exam like
1,
next
test 2, test 3. How many tests do we have?
4 tests. You mean in the course?
Yeah.
Yeah, 4.
4
So
tests.
we got one more on logistic regression,
Test.
but not next week. I think it's like 2 weeks or something.
do I need to do diagnostic test and multiple collinearity, just like assignment 3? Models tested and selection of the model for assignment 4.
Yeah, so in this case, you don't have to do like the BIF or the tolerance or anything like that, but definitely look at your correlations.
And for model tested, do I need like do I need to residual diagnosis test?
I don't think this is the logistic regression one, right?
Yeah.
Yeah, I don't ask for residuals or anything like that.
Model tested
So-
just
So the model tested like, so if
based
you,
on coefficients,
well, just generally, what were the models you tested? So what were your predictors, what were your outcomes? And so, and again, it's been a while since I looked at it. So model one, right, so here, like,
Yeah.
your model one is regression outcome versus the first predictor. Model two is on the second predictor, and then the third is on both. It's a multiple logistic regression. So that's all I'm really saying there is the paragraph on, paragraph describing the models tested.
Okay.
So whatever your outcome is to your predictors. So we tested, we fit, we had 3 models to fit the data. The first model tested this, the second model tested this, third model tested this. That's what that means. Oh, and I do have your assignment 3, so let me get those passed back. So let me get your attention just really quick here before I pass these back. So again, so assignment 3, assignment 3 is the one that you're probably gonna have the lowest score on the first draft. The reason for that is because there's so much more for that assignment. You're looking at, your, unusual observations. You're looking at your diagnostics of linearity, normality, equal variance. So a lot of places where you can lose some points. So don't be discouraged with the score that's on here. It's a draft. You're going to do a revision. You're going to resubmit it. Just take each point, address it one by one, right, and then submit your final version for it. So just know it is going to be lower than that first assignment for this draft. Don't let that stress you out. Take it on as a challenge. You got this, right? Come see me if you have questions. But just remember that, module, if you start to feel discouraged, remember assignment number 4 and assignment number 5, assignment number 5 are going to be easy in comparison. So there's that. Hopefully, hope to soothe your pain. So, all right, so let me pass these out. Yeah, I guess depending on which direction you're looking at, right? That'd be great. Oh, yeah. Maybe you gotta see Friday. Yeah, so maybe me and you. Yeah, maybe. Hey, yeah. You're right. That's okay. You're getting dressed. Oh, yeah.
No.
Okay. Oh, so in place, let's say if I have 4 comparisons like we did here today, right? Yeah, that I'll place the 2, 0. I have to adjust for it. The kid from like the last one. So I say multiply by 4. 0, 1, 2, 5. Now when I have 4 comparisons, it relates to 5. Does that make sense?
Yeah, you know.
Yeah. Right. So if I have 4 comparisons, each of them is like 25. And alpha is actually going to
I don't want that, right? I want it to be 5, that's my question. I divided it by 4. Still no.
Why did you say that?
No.
See you guys later.
Okay, you get your output, you have to remember, I did 4 comparisons. I can't use an output. That's why you're using it.
I didn't learn anything. Like I didn't know. That was
They're the same thing. These are all like this here, right? So this one is not. This one is. This one's under the board, right? So for 0.05, you could say not significant, but it's close enough that you could say 4%. Same thing with the. Just notice I'm not. Right. So. I think what you're thinking of is that we did up there. Where it was like some more, some more.
Yeah.
You could still, but really, I think we change our reference to a C. Yeah, and then that's the one where we got some issues also. No, not the fun. I keep 77. Don't recommend it if you take it 70/50 because it's like a 70% overlap that class. The only real difference is that we look at articles and say if it has us. But the content is pretty much the same. And so I would definitely check with your advisor to see if that is okay with them. Because like I said, it's the same material 70/50, except don't do HDFS. Yeah. Yeah, I wouldn't call it meaningful, but you're welcome to down if you register for it. So just realize it's going to be good. Yeah. The thing that you're going to get from the course, which may or may not be is that it is under large articles. Where they go through, look at the results, see where you can get the numbers, see if we assumptions, stuff like that. So we just carry out our questions. So go back through the same all of the new slides that we did. So a lot of redundancy. So that part of I would say that would be worthwhile, maybe that. I don't know what course code is, but it's HDFS 77. Yeah, you're welcome. Yeah. Yes, but you send me more money than I can do for them. This Friday? Sure. Maybe policy, and do that first thing. Right now, it's. Did you really? Congratulations. Yeah, that's great. Send me an email. Let me know what it was called. Was it just like graduate student award or what was it?
Yeah.
Yeah, let me know. Send me a picture. Yeah, absolutely. That'd be great. I'm so happy to hear that. That's good.
Can I come to your office? I would really do feel
No, I'm just kidding. Yeah, you can come right after. Yes.
This format,
Correct, yes. Yes, because the 2 and 3 were the same with just Yeah, multi-family added to it. So if you address these, it's gonna address those two. You can get 100%, so you can address everything, but yeah, do what you can. Yeah, do what you can do.
Friday, Friday. Okay.
Yes. Yes. Yeah, you probably.
We scaled down such your office here,
Right? Yeah, try to find something that's you're interested in, that makes it easier, but if not, you just need a logistic regression. Yeah, we can look them over and see what ones that you can address. Yeah, kind of like what we just talked about, like, you know, so three models with the data, and say, regression. It's complete. Yeah, anytime when you first say like, I'm doing three models, so you're welcome. So, here's the three models. As a reader, my first thing is, what are these? Like, otherwise, you're saying three models have nothing to do. You can, but I would still write out like all the ones look at these four predictors. So model two was when we transformed this variable. Model three was one composition. Don't need anything more than that, but just to get a reader, a visual kind of idea of what are these models. And I later see model one, model two, model three, then I know which one we're talking about, the transform model or the observation model. Do that the first time you mentioned the models, and you just talk about it as. Very good. Tell me what you're seeing, right? Because you can say, oh, it looks great, but it doesn't tell me like even what you're doing. So when it comes to like a published article, would I go into detail? Probably not, right? So for the sake of this course, I want to know that you're looking at these residual plots, regular rates. That's what you need to take from this course. So when you say something like symmetry, I can have an idea what you're talking about there. Right? That was, but when we're addressing that linearity that you're looking for. For equal variance of what in that plot that equal variance is the spread the same all the way across. So there's a funnel. One set of my state spread.
So I need to address the shape, like the planet shape, like the view shape.
Yeah.
And I also in here, I also need to address the scope which I get from the scope distance from regular distance.
Right. So you already so you have to indicate like what is your criteria for determining whether this observation is goes into. So we get that. I mean, and then what was the value? What was this value? So value for the observation of week, but also what was your criteria? So yes. Yes. Not for this. Not for this.
So I don't need reference. So
so again, so the probability, like whether or not you're rejecting all the correlation of the possible the same size. And so we're not so much interested in whether or not we reject the log, we're just interested in the magnitude. It's just very for this isn't, so I wouldn't actually be concerned about this one. So just because it's significant doesn't mean I'm concerned about it. Huge. But in this one I would be right, so I would definitely report this one.
So what do you I want to
So Friday.
Friday.
Yeah.
And that I can if that needs to writing. After taking, then I can after the solution of the system.
Yeah, that's fine. Okay, yeah, whatever.
Because
you
this week
need.
I don't.
Yeah, that's good, that's fine, that's what I say, like, pace it as you need to, I mean, at the end of the semester, it all has to be in, right? But pace it so that, you know. That's perfectly fine. Yeah, just don't get overwhelmed with the comments, just address each one at a time. Okay. Oh. How are you doing?
I'm doing good.
Yeah, your semester going all right?
I mean, all right, but I'm studying to catch up with kids.
Yeah. How's your family doing?
Sorry,
How's your family doing?
family are here. They're doing good.
They're doing good.
I mean, my daughter is getting like HF exams. this
Oh,
week.
yeah, my kids are doing the same
I
thing.
just like to help her sometimes. I'm looking for like extra, because she needs some support. I would help her, but you know, she has some homework every night.
Yeah.
But I see her at 7. At 7, she's very tired, and
Yeah.
I'm also very tired.
And, I know.
So, and the way I'm teaching her is not the way that they are learning at school.
Yeah.
But my wife is doing good. She's learning, you know, the Baptist church, our first Baptist church.
Mhm, yeah.
She's learning English over there.
That's good, yeah.
And I also go there every Wednesday evening. I'm taking care of the kids, not my kids, but the kids over there.
Yeah,
Because they're all like people learning English.
right.
But someone needs to take care of
Gotta watch the kids, yeah.
So I take with my kids and other kids over there.
Yeah.
Overall good, but
Which is good time. I know you got like lots of stuff to do, and I know I've been in that same boat too, where it's like, you know, it's good time that you have with your kids, but in the back of our mind, it's always like, I gotta grade this, I gotta write this, I gotta.
same. I also have to like grade my I mean, I have 65
Mhm.
students,
Mhm.
and my final project is 75 pages,
Yeah,
and I have 65 students. I have to make grading, give them comments.
yeah,
And if we have the master tournament, maybe another
yeah,
culture,
I do,
my
yeah.
students place.
Yeah, all my students are, like a quarter of my students are going to.
Work there, right?
Yeah.
But they have presentation, so I have to do group presentation.
Yeah, did you figure that out? Did you figure
Remember,
that out?
I
Yeah, yeah.
was asking you.
Did that work?
Yeah, I did. But they asked me, can I change my group? Can I change my group? Can I change
Right.
your group? Because you can change with someone available at that day.
Yeah.
So many, believe me, I mean, I barely, for example, you know, my tag sticker,
Mhm.
I just did it today.
Mhm.
If I was late, so I just forget it. I mean, I had to follow kids, family, money things, and my wife want to travel to Turkey. I don't want to travel, but she wants to see her parents.
Yeah.
Of course, she needs to see. I mean, believe me that if I only have the classes, it's very easy.
Yeah.
But
But when you're juggling 8 different things,
exactly.
I know, I
And
know.
also dissertation, job application, job
Yeah.
interviews, and most likely I'll be interviewed next week in person in Florida State.
Okay, that's good.
And
Yeah.
I have IRBs, not
But it's all on top of everything you got to do. Like it's good stuff. It's
Yeah,
just a
but-
lot of it,
exactly.
which I understand. Which also is why, like, I mean, I'm really flexible with deadlines and stuff because I know if you're anything like me, like you are busy all the time. So
I mean,
and I
believe me,
know
I
you
mean,
are.
and also I'm working like extra time because in our school we have like community engagement.